Okay, welcome to my 4th hour Mr. Foor algebra review. So what we're going to go over is graphing rational functions first and converting degrees to radians to degrees and learning about coterminal angles. Okay, first we're going to be learning about graphing rational functions. Okay, first we're going to start off with an easy example, 1 over x. Okay, first we're going to find the domain. The domain of a rational function is for all real numbers except for when the denominator equals 0. So for this example, we have the denominator x, okay? So when x is 0 on the bottom, that means x has to be 0. Okay, now we're going to do vertical asymptotes. Vertical asymptotes occur when the denominator of a rational function is 0, okay? That's provided that the numerator is not 0 at the same point. So since f of x equals 1 over x, f of x can be simplified to y. The denominator is 0 at x equals 0. So there's a vertical asymptote at x equals 0. The horizontal asymptote describes the behavior of the graph as x to infinity or x to negative infinity for the rational functions. If the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is at y equals 0. In this case, the degree of the numerator, which is a constant 1, is less than the degree of the denominator, which is x degree 1. So as x to infinity or x to negative infinity, y equals 0. Intercepts, x-intercept, the x-intercept occurs when y equals 0. For y equals 1 over x, the numerator is 1, and it never equals 0. So there is no x-intercepts. Y-intercepts, the y-intercept occurs when x equals 0, but since f of x equals 1 over x is undefined as x equals 0, there is no y-intercept. Okay, now we're going to do a little bit more of a challenging example. We have x squared over minus 1 over x minus 1. Okay, so again for the domain is all real numbers except for where the denominator equals 0. So the denominator in this example is x minus 1. So to find the when denominator is 0, all you have to do is plug in a 1 to cancel out the negative 1. For every question that you do regarding this, what you'd have to do is factorize, okay? So you have to factorize both the numerator and the denominator. In this example, the denominator cannot be factorized because it's already at its simplest, okay? So we have x squared minus 1 on top. So to factorize that, all you have to do is x minus 1, parentheses, x plus 2, parentheses. The factor x minus 1 appears in both the numerator and denominator, so we can cancel these factors. But note that the cancellation only works for x does not equal 1. This means the function simplifies to y equals x plus 1 for x does not equal 1. So the simplified function y equals x plus 1, except that x equals 1. So the hole in the graph, when we cancel the common factor x minus 1, we create a hole in the graph at x equals 1. This is because the original function is undefined at x equals 1, so the graph doesn't actually exist at that point, even though it behaves like a straight line for other values of x. So we know the hole is x equals 1. Okay, so now we have to find the intercepts for this little bit harder challenge, okay? So the y-intercept, all you have to do is set x to 0 in the simplified function, which is y equals x plus 1, and you would get y equals 1, okay? So that's why y-intercept is 0, 1. Now, for the x-intercept, all you have to do is set y to 0 and solve. When you do that, you should get negative 1 for this example. So that's the x-intercept. Okay, the vertical asymptote. There is no vertical asymptote since the function was simplified and there is no denominator causing division by zeros anymore. Okay, next graph. The graph will be a straight line, y equals x plus 1 with a hole at x equals 1. Okay, now we're going to do a little bit of a harder example. This example is x squared plus 3x minus 4 all over x squared minus 4. Okay, the domain is, so first you have to do the denominator x squared minus 4. You have to factor that, so that is x minus 2, parentheses, x plus 2, in parentheses. The function is undefined where the denominator is 0. Okay, so all you have to do is ignore one side of the problem. So x minus 2, you need 2 for that, and x plus 2, you need negative 2 for that. So you know the domain is x does not equal 2 and x does not equal negative 2, meaning the function is undefined at these points. Okay, vertical asymptote. Vertical asymptotes occur at x equals 2 and x equals negative 2 because the function is undefined at these points and there are no common factors in the numerator and denominator to cancel them. Okay, the vertical asymptotes, we just said x equals 2, x equals negative 2. Now, horizontal asymptote. Since both the numerator and the denominator are quadratic, degree 2, the horizontal asymptote is determined by the ratio of the leading coefficients. Both the numerator and denominator have a leading coefficient of 1 for x squared. Okay, so all you have to do to find the horizontal asymptote is ignore everything but the leading coefficients, and in this problem, it's x squared in both the numerator and denominator. So you'd have x squared on top, x squared on bottom. Okay, so when you simplify this, or whenever you divide top by bottom, since they're the same thing, whenever you divide something by itself, it's always itself, so it's 1. So that's how we know the horizontal asymptote is 1. Okay, now we have to find the intercepts. Okay, the y-intercept, set x to 0 and solve. Okay, or x to 0 and solve. So we have y equals 1. Okay, so now we know the y-intercept is 0, 1. Now x-intercept, set the numerator equal to 0 and solve. X minus 1 equals 0, so x equals 2, or x equals 1. The x-intercept is 1, 0. Okay, now we're going to do a little bit more of a simple concept, converting angles. First, we're going to do how to find radians from degrees. That's the formula on the left side, and on the right side, it's an example. Okay, so in this example, we're converting 30 degrees to radians. Okay, so basically, you're putting the degrees on top of this. So it would be 30 pi over 180. Okay, so when you do that, you just have to simplify from there, because you get 30 pi over 180, that simplifies down to pi to 6. Easiest way to do this is plug that into a calculator minus the, so that would be 30 over 180, press enter, it should give you a decimal, okay, and from there you press math, go down to fraction, click that, and it should give you the most simplified fraction. Okay, now we'll learn how to find degrees from radians. On the left side you see the formula to find degrees from radians. On the top example right here, ignore the bottom one, and that's there, we have pi over 15, okay, so that's the base radian, okay, so what we have to do is multiply that by 180 over pi, and in this example, all you have to do is, or any example I guess really, all you have to do is plug that into a calculator, and when you do that, you get 12. When you are plugging it into a calculator, make sure that you have parentheses around each one of the numbers, I guess, so you would have parenthesis pi divided by 15, parenthesis times, parenthesis 180 divided by pi, and parenthesis. Okay, so that's how you find degrees from radians. Okay, now we're going to do coterminal angles. Okay, so all you have to do is whenever you have your angle, if it's a positive number over 360, you subtract 360. If it's a negative number, then you add 360. Okay, you keep on doing that until you get over 0 or under 360. Okay, so as you can tell in this example down here, you start off at negative 330. When you add 360, you have 30. So that's how you find coterminal angles. Okay, so thanks for watching. I appreciate it.